and welcome back to our Smart Irrigation System podcast series. This is our episode 2 for podcast. So, we are going to explain our block diagram, how our sensor work, and how everything connects, like sensor to ESP, DAQ, and Labview. So if you are curious about how our system automatically control water based on soil and rain sensor, stay tuned. Okay, so Dayana, can you explain about your block diagram?
Okay, for our project block diagram, the block diagram consists of 5 main components, which is the soil moisture sensor, rain sensor, ESP32, relay and water pump, and the last one is the DAQ. So for the sensors, we connected with ESP32, and it will act as a brain of the system. And then the ESP32 will process the input and for both of the sensors. So based on their readings, it will show the data that we want to collect lah. And then it will decide whether to active the pump based on the soil condition and based on the data. Meanwhile, the data acquisition, which is the DAQ, is connected to the Labview to show the data that we will collect. Okay.
To make it simpler, the sensors collect environmental data, and then the ESP32 makes decision based on the data. The relay carry out the action turning on the water pump on and off. Also, the DAQ and Labview are there to observe, record, and analyze the data. It's like having a small brain ESP32 and a big screen in Labview to watch everything happen live.
Exactly. And one thing to note is all components share a common ground connection, which is very important for accurate data measurement and system stability. We also use buffer circuit and voltage divider to make sure the voltage level from sensor are safe for the ESP32 ADC input. This help prevent incorrect reading or damage to the microcontroller.
Okay, Hulai, can you share with us how soil moisture sensor work?
Okay, now let's talk about our first sensor, the soil moisture sensor. This sensor measure how much water is in the soil. It used two metal probes that act like electrodes. When these probes are inserted into the soil, they measure the resistance between them. If the soil is a lot of water, it conduct electricity well. So the resistance is low. If the soil is dry, it resists electricity, so the resistance is high. The sensor then outputs an analog voltage that change according to the soil moisture content.
Right, and that analog voltage is read by the ESP32 ADC, which converts it into a digital value between 0 and 4095 because the ESP32 uses a 12-bit ADC. So we calibrate the sensor to find what value range represents, which is dry, moist, and wet conditions. For example, below 1200 might mean dry soil, between 1200 to 2500 is moderate moisture, and above 2500 means wet soil. And this helps the system make accurate decisions automatically.
So we also tested the sensor in different soil types. such as sandy, loamy and clay. So each one of them shows a different values of data that we collected, and because it is based on how they hold water differently. And then that's why calibration is also important. And one more thing, we avoid leaving the props in a wet soil for too long because corrosion can affect the accuracy. So that's why we use a protective coating to reduce this problem.
Okay. Can I know how raindrop sensor work?
Okay, let me explain about it. So the second sensor we use is the raindrop sensor. How it works? The first thing is the sensor is look like a small flat board with a conductive on the surface. So it's like a circuit for when the rain drops on the board. So when it's dry, there's no connection between the lines, so the output voltage is high. When the rain drops on the plate, they form a conductive path, allowing current to flow and the voltage output drops. So basically, more water, lower output voltage.
And then this sensor use LM393 module that give both analog and digital output. Analog output to measure rain intensity, and then digital output to measure to detect rain percent. And then we use one signal in your project, more better and flexible detection.
And similar to the soil moisture sensor, the raindrop sensor also need calibration. We adjust a potentiometer on each module to set the sensitivity, so it doesn't trigger too easily from few drop or humidity.
Okay, now let's put everything together. Number 1, boost soil moisture and raindrop sensor continuously send signal to the ESP32. Number 2, the ESP32 ADC convert those signal into digital values. Number 3, based on preset condition, the ESP32 decide whether to activate the water pump or keep it off. For example, if soil is dry and no rain detected, the ESP32 will activate the relay and turning pump on. And if soil is wet or rain detected, the relay stay off, pump will turn off. This helps save water and ensure plants only get water when needed.
Exactly, and the relay module acts as the switch between the ESP32 and the water pump. The ESP32 cannot handle high voltage directly, so the relay isolate and control the pump safely. We use a 5-volt relay module with an opto isolator which protects the microcontroller from high voltage spike.
Once the relay is triggered, it completes the circuit for the pump's power supply, allowing water to flow. When the ESP32 deactivates the relay, the circuit opens and the pump stops. This entire process happens automatically without any manual input.
Okay, Aiman, can you explain integration with DAQ and Labview?
Okay, thank you, AFFIQ. The DAQ device collect sensor data and send to Labview. We design GUI showing soil moisture and rain status and water pump operation in real time.
Okay, so while the ESP32 does the control automatically, the DAQ and Labview act as our observation tool, which is helping us confirm that everything works correctly and record data for our report. And it's like the system has two brains, one for control and one that monitor.
We also use Labview to analyze sensor fusion performance. For example, checking how accurate the system is when both sensors detect change at the same time. This helps us fine-tune the threshold for better accuracy.
So to summarize the process, 1. Sensor collect the environmental data. 2. ESP32 read and process the signal. 3. Relay control the water pump automatically. 4. DAQ and Labview monitor and record data. It is an efficient, low-cost system that can be scaled up for real agriculture use.
We also learn a lot about sensor calibration, ADC resolution and signal conditioning while building this project. It wasn't always smooth. We had to troubleshoot noise, incorrect readings and even voltage mismatch, but we solved them through testing and adjustment.
Okay, that's bring us to the end of episode 2 and our technical deep dive into how our smart irrigation system work, and we cover the sensor ESP32, DAQ, Labview and the overall process. Thank you for watching.
See you
See you in the next